So this is my lecture 6. So in my lecture 5, I discussed about lead controller and derived some algebraic condition to design the controllers. Now we will be discussing lag controllers. Lag controllers or compensators. Lag compensators. So lead compensator, we saw that lead compensators are used to provide phase lead as well as gain amplification. So lead controllers are used to speed up the response, or if a system suffers from poor phase margin or damping ratio, because phase margin is equivalent to damping ratio, then lead controllers are used. Now, under which situation lag controllers are used? So lag controllers are used I will use different ink. So used to provide gain attenuation. So this is the main objective. Gain attenuation at a particular frequency. So this is the main objective. But at the same time, when you are providing some gain attenuation, that means you are lowering down the gain curve of an uncompensated system. So at that time also you have to provide some phase lag. So in this process, that means when you are providing attenuation at a particular frequency, gain attenuation, at that time also you have to provide some small amount of phase lag. So also used, that's why I'm writing also used to provide small amount of, but this is not the objective. The main objective of lag compensator is to provide gain attenuation. Okay, so anyway, I'm writing also used to provide small amount of phase lag. So remember that this amount of this small amount of phase lag has to be provided to achieve the objective of gain attenuation at a particular frequency. Okay, so that means under which situation. So these are the so lag compensator will provide some gain attenuation and phase lag at a particular frequency. Now under which situation you will use? So if a system if an uncompensated system, if an uncompensated system suffers from phase lack of phase margin. Uncompensated system suffers from lack of phase margin. Then that means simple plant is there, and the unity output feedback, unity feedback loop suffers from margin, then lag compensator can be used to compensate them. Lag compensator can be used to compensate them, but at this process, but the gain cost of frequency is reduced, but the GCF or speed of the response is reduced. So also lag compensator is used, to make the system response slow. If your system response is very fast and you want to make it slow, then lag compensators are used. So, but the main thing is that your system does not satisfy, suppose your phase margin specification, then you can one way to then you can compensate them to achieve some to achieve the phase margin. But at the time, what you have to do? You have to reduce the speed of the system. That means gain cost of frequency you have to reduce. That means gain curve of the uncompensated system you have to make it down so that desired phase margin you will get. So once the gain curve you will make it down, what will happen? The gain cost of frequency will reduce. So then what advantage you will get? Your phase margin will increase. So this is the main use of lag compensator. So lead compensator, what lead compensator will make? Lead compensator will make the system fast. That means gain cost of frequency at the time. So lead compensator increases phase margin by providing phase lead. Okay. So and the lag compensator compensates for phase margin by lowering down the DV curve. So this is the main two difference between lag and lead. Lag compensator, again and again I am saying, lead compensator provides phase margin by shifting the phase curve, by increasing the gain cost of frequency, so that the phase margin can be met. That means it is making the system fast. But lag compensator will make the system slow. How it will make slow? It will lower down the DV curve so that phase margin is achieved. So this is the philosophical difference between lag compensator and lead compensator. So main is gain attenuation here, not phase lag. Main objective of phase lag compensator, although the name is lag, but actual job is to attenuate, provide attenuation, gain attenuation at desired frequency. But when you are providing some gain attenuation, some phase lag will automatically occur. So that phase you have to provide, that phase lag we have to provide by the compensator. So now what is the transfer function? So transfer function is what? HS equal to 1 plus S by. So here 0 less than beta less than 1. So this is the difference between lag and lead. In case of lead compensator, beta was greater than 1, or at the time we considered alpha. So it was greater than 1, now it is less than 1. So this also you can write in this form. So that means your HS will be beta into S plus B divided by S plus beta B. So now what is the pole zero map here? So the pole zero map for this controller is this one. So suppose your sigma j omega. So here your beta is less than 1, so your pole will be closer to the imaginary axis. So that is the difference. In case of lead controller, 0 is closer to the imaginary axis and pole was away from the imaginary axis. But here pole is closer to the imaginary axis and 0 is away from the imaginary axis. So this is pole Z, PZ map, pole zero map of edges. Now what is the Bode plot? Here Bode plot you can also draw. Bode magnitude plot. So Bode magnitude plot, if you draw lag compensator, this is your omega. So suppose this is your 0 dB line. This is your 0 dB line, and then you, from the transfer function you can see there are two corner frequency. One is B, one is beta B. So beta is less than 1, so beta B will come first. So this is suppose your beta B, and this is suppose your B. Then what will happen? Because of this this 0 first, because of that 0, no, first the pole will dominate because pole beta is less than 1. So because of this pole, first minus 20 dB per decade slope will be there. So here, so it will look like this. So here minus 20 dB slope will be there, get nullified by the 0 location at omega equal to B. Minus 20 dB per decade slope, and then it will get nullified. So this is your asymptotic magnitude, Bode magnitude plot of lag controller. So this is 0, and this, what is this magnitude? This magnitude will be 20 log of beta, because the slope is minus 20 dB per decade, this slope. Okay, so now this is your Bode plot. As from the Bode plot you can easily see that in this frequency range, so here gain is unity, but in this frequency range it is providing attenuation. Gain is negative because beta is less than 1. Now if you draw the phase plot will be like this. So phase plot will be like this. So at omega equal to 0, phase is 0. As omega equal to infinity, phase is also 0, because phase is what? Here tan inverse omega by b minus tan inverse omega by beta b. So when omega equal to 0, phase will be 0, phi, and when omega equal to infinity, pi by 2 minus pi by 2. So at the time also will be 0. But in between, what will happen? In between, because beta is less than 1, phase will be negative. So it will look like this. You can draw also asymptotic phase plot. that I am not drawing. Okay. So this is your phi m. That is the minimum phase, maximum phase lag it will provide. So, and this is your again, so this is beta b, and this is so this frequency, the frequency at which it will give maximum phase lag will be again geometry mean of. So here all the things are similar to or same as lead controller. The only difference is here beta is less than 1. So it will be root beta into b. Okay. What we have got, omega m, we have got omega m is b root beta. And what is your maximum phase margin? Phase margin, maximum phase margin. So if you see, it will be that earlier lead controller formula, it was alpha minus 1 by alpha plus 1. So here now it will be beta minus 1 divided by beta plus 1. So now since beta is negative, so phase phi m will be negative. So this also you can write, this is equal to minus sine inverse 1 minus beta divided by 1 plus beta, where so here beta is less than 1. Okay, so as beta is less than 1, this implies that phi m is negative. So phi m is negative. So now how to design this lag controller using the algebraic approach as we have done for lead controllers. This algebraic method is important, as I said earlier, that in most of the books they have followed some iterations, some assumptions, but here in educational book only so he had provided some good algebraic method, so that I am following. So the algebraic method to design lag controllers. So what is the objective? What is the object? Only derivations I will make here. So what is the objective that we should know? So given phase lag phi c. So phi c, remember that phi c here, phase lag means phi c is negative. Phase lag means here phi m is negative. Any phase lag that will provide, that means phi c is negative. So and given phase lag phi c and attenuation MCDB means that is again MC is negative. Remember that. In case of lead controller, phi c and MC both are positive. Okay, MCDB means attenuation means negative. So negative in dB. So at frequency omega c, what is the problem given? So what are the given? Phase margin phi c and attenuation MC in dB. We have to add some frequency omega c. We have to obtain the controller parameter. What are the parameters? Beta and b. Okay, so what is beta? Beta we have seen that here b is greater than 0. B we are assuming greater than 0. So b we are assuming greater than 0. And so in case of here also that A and lead control, I cannot remember whether I have written or not, so that is there A is 0. If you consider B is 0, then the things will be B less than 0, the things will be complicated. So for convenience, B less than 0 means it will be unstable system. So unstable non-minimum phase plant. So all sorry, non-minimum phase controller. So those things we are not considering. This simple thing we are considering. So whatever controllers normally we design, controller will be minimum phase and stable. That is always expected for a practical system. Controller is avoided to be unstable, as well as non-minimum phase. So unstable controllers are not allowed in practice. So this is beta and B. So now what is the solution? So solution is, so now you will see that the here all the things are same, like lead controller. So only difference is beta is less than 0. So the same final quadratic equation you will get, where alpha will be replaced by just beta, and MC here negative and phi c is negative. So the quadratic equation now becomes the quadratic equation as we have obtained in equation 5 in case of lead controller. That equation will now become, the quadratic equation now becomes what? Q square minus C plus 1 into beta square plus 2Q square C into beta plus C into Q square C plus C minus 1 equal to 0. So what I have done, only I have replaced alpha by beta. In equation 5 of lead controller, I have only replaced here alpha by beta. So now, so here also, see, so we have to first guarantee what is the condition for a positive, because beta is positive, but beta is less than 1, but it is positive. So first we have to obtain a condition for beta greater than 0, for a condition for existence of a beta greater than 0. Then we'll see whether that condition suffices. That condition also ensures that beta is less than 1. Beta is positive as well as less than 1. So first we will see what is the condition for which beta is positive. So now, similar to that earlier one, so in case of lead controller, so as here Q square C greater than 0, for a positive solution to exist, positive solution of beta, positive solution of beta to exist. What is the condition? Here, positive solution to exist. So it is, as I said, in case of lead controller, you can compare this equation like compare the equation with a standard second order equation, that is ax square plus bx plus c. So suppose b is greater than 0, like here q square c greater than 0, b is greater than 0 suppose. Then what is the condition for existence of at least one positive root? There it will be a into c will be less than 0, as I discussed in the last class. So here also, a, what is here? A is this one, and what is your c? C is this whole term. So for a positive solution of beta to exist, what is the condition? Q square minus c plus 1 into Q square C plus C minus 1 into C should be less than 0. Now the situation, now now we'll see what is your C. Now, what is your C? C equal to 10 to the power of mc by 10. Earlier also we consider this is your C. mc is in dB, that is gain at, so mc is negative. So as mc is negative, so this will be less than 1 now. In case of lead controller, it was greater than 1 because at the time mc was positive. Phase and gain amplification. So now gain attenuation. Gain attenuation means gain negative in dB, or in terms of unit place, it is gain less than 1, gain greater than 1. So it is now MC negative. So that's why this is less than 1 that I am writing, since MC negative in dB. And what about Q? Q equal to tan of phi c. Tan of phi c. So this is also less than 0. Why? Because phi c is negative. Phi c negative. So Q is less than 0. C is also less than 1. C is less than 1 but greater than 0 because MC is so 10 to the power MC by 10 cannot be less than 0. So this is C lies from 0 to 1. So then what will happen? Q square C plus C, sorry, this one. Then you can see, so Q square minus C plus 1. So 1 minus C will be, 1 minus C will be now greater than 0. Q square is greater than 0. So Q square minus C plus 1 will be greater than 0. Therefore, for a positive solution to exist, positive solution of beta to exist, what is the condition? For a positive solution of beta to exist, the other factor should be, this factor should be less than 0. This factor should be less than 0. Now C is again greater than 0. So C is again greater than 0. So that's why this Q square C plus C minus 1 should be less than 0. Q square C plus C minus 1 should be less than 0. So here, okay. So since here again I am writing since C greater than 0. So this will imply what? C should be less than 1 by Q square plus 1. So this is the necessary and sufficient condition for positive solution of beta to exist. Now we have to see whether this condition will also guarantee that beta is greater than 1, sorry, less than 1, as we have seen in the last class, that this that condition at the time we obtained condition that Q square is less than Q square was I think less than C minus 1. Q square was less than C minus 1, and that also guaranteed alpha greater than 1. So now we have to see that whether with this one beta is so positive solution exists means so now we have to see that whether positive solution exists means C will be beta will be less than 1. So that you can easily see from this one. So this is, I will write necessary and sufficient condition for the time being for positive solution of beta. So now if you see your main quadratic equation from 1, so this is your 1. From 1 you can easily obtain, from 1 if you see 1, then 1 can be factored like this. If you take, say, this one, so q square. So q square, if you take common, suppose 1, you can easily write q square from 1, q square into, if you see equation 1, it was it will be q square into beta plus c. Please check whether I am correct or not. Beta plus c, equation 1 can be written like this: q square into beta plus c whole square equal to c minus 1 into beta square minus c. Actually, this equation was also there just before equation 5 of a lead controller. There it was in terms of alpha. Now it is just alpha I have replaced by beta. So from this equation, you see left hand side is greater than 0. So also c minus 1 is what? C minus 1 will be now c minus 1 is less than 0. So beta square minus c. So this implies beta square minus c has to be less than 0. Why? Because this left hand side is greater than 0, greater than equal to 0, and c minus 1 is less than 0. So so this implies your beta square less than c. Again, c is what? Less than 1. This implies if a positive beta exists, then, so here beta can be negative also, but if a positive beta exists, that beta will be less than 1. So this implies if a positive beta exists, then it will be less than 1. So that means this is also necessary and sufficient condition for existence of lead controller. That means, again I am writing, therefore, so that means positive. So you need not to bother about whether beta less than 1 or not, beta less than 1 exists or not. Because a positive beta exists means there it will be less than 1. So less than 1 is inherited from the quadratic equation, equation 1. So therefore c less than 1 by q square plus 1, c less than 1 divided by q square plus 1 is necessary and sufficient condition for existence of lead controller. Sorry, lag controller. Lag compensators. Compensators and controllers are same, only terminologies are different. Compensators, or sometimes filter, it is also called in signal processing context. So this is the situation. So now suppose you have found out once beta you find suppose, so what is the steps? So given phase attenuation and phase lag and gain attenuation at a particular frequency, we will first check whether this necessary NS condition is satisfied or not. Then only lead compensator can be designed. If it satisfies, then what will you do? You will solve this equation and you will take a value which is positive value of beta, because positive value of beta will automatically guarantee it will be less than 1. So positive value of beta you will get, and once positive value of beta you will get, then what will be your beta you can obtain. Now the remaining is B. So how you can obtain B? So once beta is obtained by solving one can determine B equal to same thing like lab compensator. We have used the same this equation for computation of A. So here we have termed that one as B. So W by omega C by beta, the same derivation for deriving this one, beta square minus C divided by C minus 1. So in the lag compensator, in the lead compensator, B was A and beta was alpha. So that's the difference. So that means these three things are important. One is this one is this one, and this one. Okay. These three equations are important for lag compensator. And as I said, lag compensator, the main objective of lag compensator is to provide gain attenuation. So while providing gain attenuation at a particular frequency, it also provides some phase lag. Although it is not accepted, phase lag is not accepted, but we have to accept that phase lag it will provide. Phase lag is not desirable. Phase lag it is providing, but phase lag that we have to accept. Phase lag it will provide, but ultimately overall phase margin can be improved. Compensator system phase margin, because gain curve it is making gain curve it is lowering down, so gain cost of frequency will increase. So overall, although it will provide some phase lag, but overall phase margin will increase. And that all these things we'll see through one example. So one example I will consider which will cover all the designs: lead, lag, lead. So it will be a very interesting example. So just for the timing, whatever steps I have discussed to design lag controller, so I will consider a small example. So design a lag controller. Design a lag controller, so that will provide a phase lag of. So here although I have written 50 degree, but that much phase lag we will not normally phase lag will be 10 degree, 15 degree, like that. So just for numerical illustration, we are considering this example: phase lag of 50 degree and attenuation of 15 dB at 2 radian per second. So solution. So here, what is your phi c? So phi c will be minus. Phi c is your phase lag. So phase lag of 50. So phi c is negative. Phase lag. So 50 degree. And what is your MC? MC is, as I said, MC attenuation 15 dB means MC equal to minus 15 dB. And omega c is what? Omega c equal to 2 radian per second. So this will imply what is your Q? Q equal to again tan of phi c. So tan of phi c equal to minus tan 50 degree. Tan 50 degrees. So this will be, if you compute, it will be minus 1.192. And what is C? C will be equal to 10 to the power of MC by 10. So the same C we have defined as the same C that we have defined in your in case of lead controllers. So C will be here in case of lag controller also. C is MC by 10. Only MC is negative here. So this will be equal to 10 to the power of minus 15 by 10. So this will be equal to 0.0 316. So I suggest you to check all these calculations. I have already checked, but still there may be error. So now the quadratic equation, because in Enkeshina book the problem is that there are so many plus minus, there are many mistake, plus minus and all these things. I think typos. So those things I checked all the things properly, but still there may be some mistake. So anyway, so now the quadratic equation becomes, now the quadratic equation becomes q square minus c plus 1 into beta square plus 2q square c beta plus q square c plus c minus 1 into c is less than 0. So this will make, so even okay, quadratic equation before, but before solution of beta, we'll just check whether this the pair of phi c, the triple of phi c, mc and omega c given, whether the with those data, whether we can design the lag controller at all or not. So that means whether this condition is satisfying or not. So c less than q square 1 divided by q square plus 1. So q square plus 1 will be q square plus 1. You can easily see that your c less than this condition, c less than q square plus 1 is how much? 1.192 whole square plus 1. So approximately just greater than 2. And what is c? So that means this is 1 by 2, 1 divided by q square plus 1. So 1 by 2, that means 0.5, and c is 0.0316. So this is much less than 0.5. So the necessary and sufficient for existence of lag control is satisfied. So this equation can be solved for a beta, positive beta but less than 1. So one can easily verify, one can check that the n and s condition is satisfied. So this implies lag controller can be designed. So if you prove the data of q and c, then your ultimate equation will come out to be like this from here. 2.3887 into beta square plus 0.0898 beta minus 0.0292 equal to 0. So this will, the valid solution will be 0.09. So another negative solution will be that negative solution we will not consider because beta is greater than 0. So it will automatically become less than 1. Is 6. So then b will come out to be, then b equal to omega c by beta into beta square minus c divided by c minus 1, and this will be 3.295. So ultimate answer, the lag compensator. So the lag compensator is your HS equal to beta into s plus b divided by s plus beta b. So if you simplify, if you put those b and beta values, then it will be 0.09336. I think this is 13336. Please check it. So this is s plus 3.295 divided by S plus 0.3076. So this is about lag controller. So now one implementation, as we have said in case of lead controller. So how to implement in an analog fashion. So this is the main advantage of lag lead and lag lead controller. So that's why they are used in industries, because they can be implemented in an analog fashion, in a digital fashion easily. There is first order controller, lag and lead. Lag lead controllers, of course, second order controller. First order for lag part and first order for lead. So this is the beauty of lag lead controller. Low order controllers are easy to implement in an analog fashion. But of course, nowadays, because of those microprocessor based implementation, so even very complex controllers you can also implement in a digital processor. But earlier, those things were difficult. So an implementation of lag controller, an implementation of lag controller. So we'll see that unlike lead controller here, no non-inverting amplifier, no amplifier is needed, no feedback amplifier. So here only the passive circuit will suffice. This is R1, this is R2, this is C, and this is V1, this is V2. So we have to show that V2S by V1S structure is like it will the transfer function between transfer function from V1 to V2S will act like lag controller transfer function. So if you just check what will be your V2 by V1, so V2S by V1S will be what? So what is the current through it? Current through this loop? Current through this loop will be V2 current through this loop will be V1 divided by R1 plus R2 plus 1 by CS. So what is the voltage then? This voltage R2 plus 1 by CS into that current. So R2 plus 1 by CS into that current. What is the current? Current was V2. Sorry, current was well. So I will bit in more detail. I will do. So suppose this is your I1. So what is your I1? I1S will be equal to V1S divided by R1 plus R2 plus 1 upon CS. So this implies V2S is what? V2S is equal to I1 into R2 plus 1 by CS. So this implies V2S by V1S, V2S by V1S, that means equal to R1 plus R2 plus 1 by CS divided by your V2 by V1. V1 equal to this into RAS, so divide by your transfer function is V2 by V1. So V2 by V1 is what? V2 by V1. So here I1. V2 by V1 will be V2 by V1 will be R2 plus 1 by S divided by So I1 just you will multiply I1 equal to V1 divided by this one. So V2 by V1 will be R1 plus R2 plus 1 by CS. So this I want to represent like beta into S plus B divided by S plus beta B. So I have to represent it like this: V1S divided by V2S divided by V1S. This is equal to S R2 into C plus 1 divided by SC into R1 plus R2 plus 1. So this you can write like this: V2S divided by V1S. So this is equal to, if you take R2 into C common, if you take R2 into C common, then what will happen? It will be S plus 1 by R2C. And if you take here also R1 plus R2 into C common, then what will you get? S plus 1 by R1 plus R2 into C. So that means CC will get cancelled. So this implies V2S by V1. If I want to represent in terms of lag controller transfer function, that means beta into S plus B divided by S plus beta B. Then what is your beta? So beta is then where beta is what? R2 divided by R1 plus R2, so which is less than 1 as expected. Also less than 1 and greater than 0. Less than 1 and greater than 0. And so that is less than 1. And your, what will be your B? B will be your 1 by C into R2. Yes, then it is coming. So that means this circuit represents lag controller. So as one comment, that means note. So one note is no feedback amplifier is needed. No feedback amplifier that is needed here. Yes. Okay. So this is about lag controller. Now lead lag or lag lead, which one we will want, that we have to discuss. So just I will give an introduction of lead lag and lag lead controller. So lag lead, first of all, the question is why, whether lag lead or lead lag. So which one we have to use? So there's so many questions are there. So lag lead. So lag lead we will first discuss, and then we will say why lag lead, why not lead lag. So lag lead controller. Lag lead controllers. So we saw that if we use, so ultimate objective is that to obtain a phase margin, certain gain crossover frequency, obtain some phase margin, gain crossover frequency using lag lead and lag lead controller, because that steady state error specification will be made by the servo gain K, as we said. So using the normalized part of the controller, that means that we are considering as HS. So using that HS, what we want to do, we want to obtain only two specifications, that is phase margin and gain cost of frequency. So using lead compensator, we saw that the system will become very fast. Gain cost of frequency, it will increase because it will provide phase lead as well as gain amplification. So in case of lag compensator, what will happen? Phase margin can be met by providing gain attenuation. So using lead compensator, system will become very fast, and using lag compensator, system will become very slow. So now the question is whether in between we can obtain or not. So in between means what is the requirement? So the lead controller, the main job is to provide phase lead. That means positive phase. And lag controller, the main job is to provide attenuation. So we should have a controller. If we want to trade off between the two performances, that means lag and lead, then we must have a controller which will provide the both things together. That means phase lead as well as gain attenuation. Got it? So we want to have a behavior in between lag and lead controller. For that, phase lead is required as well as gain amplification. Phase lead is required as well as gain attenuation, not gain amplification, because phase lead controller, the main is phase lead, and in case of lag controller, the main object is avoid attenuation. So if we want to mix up these two things, we want to have if we can provide some phase lead as well as some gain attenuation at a particular frequency, then our job is done. So we'll be able to obtain a performance, able to obtain a gain cost of frequency along with desired phase margin, and that gain cost of frequency will not be much high as well as it will not be much low. So it will trade off the things. So that's why lag lead controller. So whether it will be lead lag or lag lead to provide gain attenuation as well as phase lead, that we will see. So here the objective, as I said, this is used to provide phase lead as well as gain attenuation at a particular frequency. So under which situation, so these are all technical terms, under which situation we'll use lag lead, as I said. So if you see that using lag controller, my system response is very slow, and using lead controller, system response is very fast, then we'll go for, if we are not satisfied with that, then we will go for lag lead controller. Otherwise, unnecessary, we will not increase the controller degree by 1. Also, the design is complicated in case of lag lead controller. We will see that one. Okay, so just I am writing here for convenience. So used to trade off the performance of lag and lead controllers. Performance between lag and lead controllers. Performance between lag and lead controllers. So now what is the transfer function? So transfer function lag lead controller. So HS, one will be lag part and one will be lead part. Whether lag part will be fast or lead part will be fast, that we'll see. So one suppose lead part fast. So here when I am writing whether it is lag part I am writing fast or lead part I am writing fast, that does not matter. But the magnitudes parameter values matter. So suppose I am writing lead part first, 1 plus S by A divided by 1 plus S by alpha A. Okay. So and this is, and the lag part is 1 plus S by B divided by 1 plus S by beta B. So now this parameter should satisfy some condition. So one is, so this is, if this is your suppose lead part, lead, and this is your suppose lag, then where what we should have, of course alpha should be greater than 1. Okay, alpha should be greater than 1 and beta should be less than 1. Okay, alpha should be greater than 1, beta should be less than 1. So now whether, okay, these are now still these two are independent. Now whether A should be more than B or less than B, so that is important. Now here we will see that A should be greater than B. Also for our convenience, so we'll, instead of taking these two parameters, we will assume alpha beta equal to 1, so that if we can find one value, then other value will be automatically known. Okay, this is not required. This is done for simplicity, because anyway it is a normalized controller. So instead of taking this alpha beta differently, we will consider alpha beta equal to 1, so that if alpha is greater than 1, automatically beta will be less than 1. That can be guaranteed. Okay, so this is your redundant. So that's why, that means if once you are considering alpha beta equal to 1, then you need not to specify beta less than 1, because beta automatically it will satisfy. So now why A greater than B I have assumed, that is the important thing. So A greater than B. So before that, just I will quickly draw the pole zero map. So pole zero map. So here I have considered your A is greater than B. So this is your suppose minus A. A is greater than B means suppose this is your minus A. This is your minus A. So this will be your minus B. So what is your beta B then? Beta is less than 1. So beta B will be here. So what is your minus alpha A? As alpha is greater than 1. So this will be minus alpha A. So this is your PZ map of HS of lag lead controller. So now, so still I have not said why A greater than B. So now you will be understanding from that one. You will understand from board plot. So that I am doing now. So board plot lag lead controller. So if you see here with this, that one, your whatever parameters values we have range we have assumed, your dB curve will look like this. What are the corner frequency? One is beta B, and then B, then A, and then alpha A. So the, if you see, first will be your lag part. Lag part is first according to the chosen ranges, chosen A greater than 0 or A greater than B. Because A greater than B, your lag part will be first. So why lag part first is needed, that is very important. That we will see. So if you suppose A greater than B, and then this is this one, and then it will be flat, and then again minus 20 plus 20 dB per decade. Okay, so this is the asymptotic Bode magnitude plot of lag lead controller. So this is a magnitude, this is a dB. Okay, and what is this value? This value. So now you will understood. So why I have considered alpha beta equal to 1. So alpha beta equal to 1. So that is why this magnitude is flat here through from A to B. So this magnitude is 20 log of beta. Okay. So now what is your phase? What is your phase plot? Phase plot is interesting. So phase plot will be like this. First lag. So lag peak will occur somehow here. Here also somehow here. So here that means the lag peak will be like this, and then sorry, my drawing is not correct. And then it will go like this, and it will be like this. So your phase plot is like this. Okay. So now you can see what is the objective here. Objective is to achieve phase lead as well as gain attenuation. So then in which range it should operate? The range of operation, the region of lag lead controller will be operating. So this is your operating region. Because here you can see gain attenuation you will get as well as phase lead you will get. So this is the operating region. Operating region of lag lead controller. So now if you see, if your A is greater than B, that means lead is first, then lag, then what will happen? Then at that time what combination you will get? You will get phase lag and gain amplification. Phase lag and gain amplification combination will get. That means straight opposite kind of combination you have to have. So if your A is greater than B, sorry, A is less than B, then you will get phase lag and gain amplifications, which will not be of any use as far as control literature is control design is concerned. So here the objective is to obtain phase lead as well as gain attenuation. So for that, lag part should be fast, then lead part. So that's why the controller name is lag lead, not lead lag. Although it naming is doesn't matter, but here the strictly is that lag part in Border magnitude plot, lag part should appear or appear first, then lead part. Okay, that means B should be less than A. This is the reason. This is very important thing. So this is so lag lead controller is used to trade off the performance of lag and lead controller. So, well, in the next class we will show how to design this controller using algebraic method, as we discussed for lag and lead controllers. Okay, I think just once again I will see if there is any small mistake. This is 0 dB. This is 0 dB. I think it is fine. This is less than q square plus 1. Well, okay. So thank you.